various scripts and various modalities such as printed, handwritten, scene text, video text. Shown here is a result of running a commercial OCR on this document image, which gives you bounding boxes of words and lines and respective transcriptions. On a higher level of abstraction, another problem of interest to us is layout analysis. We would like to know the group of pixels that form a heading, a table, or a graphic in the image. Recent years have seen an interest in the community for higher level document understanding tasks like understanding a table or parsing an invoice to get information from this. Shown here is in the given document image, you have a table and you might probably be interested in understanding the table to extract information from that particular table. Here we show how different bottom-up tasks such as OCR, understanding a table, or understanding what is a heading, or they all contribute to extract a particular information from this image. For example, here, to understand when the fax is sent, you need to connect information from multiple document objects or multiple layout objects. To summarize what we have seen in the previous slides, here are some important research works from the recent years that concern with various low-level, what we call as low-level document understanding tasks such as OCR, layout analysis, and segmentation. In recent years, there is an increased interest towards problems that look beyond the traditional tasks of OCR, segmentation, and layout analysis. Works in table understanding, invoice parsing, extracting tables from charts or plot, and recognizing mathematical formula from document images. There is an increased interest in recent years towards these tasks. That is quite visible if you look at the challenges in ICDAR in the last two or three editions. We pitch DocVQA as a natural next step in this direction. Goal of DocVQA is purpose-driven information extraction from document images. We aim to take a top-down approach, different from the traditional bottom-up approach, where the research is primarily centered around multiple low-level document understanding tasks. We would like to extract information from a given document image or a document collection guided by a natural language question. So far, we have introduced 4 different tasks and data sets for this. We can generally classify them into two categories. One is asking questions given a single document image, and another is asking questions over a collection of documents. Now, let me quickly walk you through the agenda for the day. The program is organized into 3 sessions. First session is related to DocVQA challenge. Then we have invited talks and a panel discussion. Ruben will introduce the DocVQA tasks that were part of this year's DocVQA long-term challenge. A summary of submissions and analysis of the results will be presented by Ruben. Followed by Ruben's introduction are presentations from the winners of different tasks. From 2:30 to 2:45, ApplyKI group will present their winning entry for task 3, followed by it is a presentation from IG Bird team from NTT Corporation in Japan who were runner-up for task 3, that is Infographic VQA. Last presentation in the challenge session is from Infrared Radar team who won task 2. The session will be chaired by myself and Ruben. Our first invited talk before the coffee break is from Brian Price, who works with Adobe. He will be talking to us about his experience in building datasets and models for chart understanding. Chair for this talk is Professor Faisal. After the coffee break, we have our second invited talk by Amanpreet Singh of Facebook. Aman has been working on DocVQA. He is also one of the main developers behind MMF, a PyTorch-based framework for research into multimodal problems in the context of vision and language. Professor Seichi will be chairing this talk. In the last invited talk, Lucy will be talking to us about her research in Microsoft on building multimodal transformer-based architectures for DocVQA. Dr. Anand Mishra from IIT Jodhpur will be chairing this talk. The last item for today is a panel discussion moderated by Demos. Our panel members are Anand Mishra, Brian Price, David Doorman, and Philip from Applica. Once again, we thank everyone for joining us today. We hope the workshop brings out thoughts and inputs that motivate future directions of DocVQA research. I now welcome Ruben to talk about the ICDAR 2021 long-term challenge on DocVQA. Thank you.
Thank you, Minesh.
Oh no, that's not so good. Sorry. Why does it use a presenter mode? Sorry.
It's fine.
Okay, I think I will just start again. I hope I can. No. I have to. Yeah. I have to switch it here again. And then we have in Zoom to share the screen. And, sorry, we have a small issue I have to fix. It says open system preferences. But it doesn't open them. Yesterday, this notebook had been used, to my knowledge, but it had. Anyone a Mac user who knows how to quickly open the? Because normally when I should click here, it should open the system preferences, but it doesn't. Or is it? Ah, they're open but hidden. Okay.
You have to click the locker icon.
Yeah. Thank you. Now. Okay. I'm very sorry, but now it should be working to share the screen. Okay, yeah, that's the desktop one. Now I would really like in the slideshow to not use the presenter view. But this is, it says here presenter view, but this is now actually using the presenter view. So now in Zoom, I have to make a new share to share the right screen. No, it's the right screen, but do you have sound or not? Anyways, I share the sound. Or maybe. Okay, I just close this. The problem is it's good.
Okay.
You can see it, yes? Sorry.
Okay, so everyone can listen to me?
Yes, Ruben, you are audible, yeah.
Okay, thank you very much. So I'm gonna present the competition that we have held in this document visual question answering. So as Minesh has said, the DocVQA challenge series started last year, And currently we have 3 different tasks. The first one, which is on infographics, the second one, which is on the document collection visual question answering, and single document visual question answering. I will explain each of them one by one. First of all, infographics visual question answering, we have to understand what is an infographic image. Infographic image is a graphic visual representation of information, data, or knowledge intended to present information quickly and clearly. This means that it contains text, numbers, and symbols, but not also that, but also complex figures like maps, pictograms, and graphics and figures. And when I mean pictograms, okay, for example, are things that are in between drawings or sketches or real images. For example, to all of us, it's easy to understand that this is a house, but it's not the image of a house, but neither the drawing or a sketch of a house. So it's a different domain. In addition, in these infographics, there is some implicit information, like the text style, the element colors, and where the elements are placed, which indicates some information. For example, if we find different elements with the same style and the same color in different places of the image, probably these 2 different elements have some kind of semantic relation. Also, the images you were seeing here are crops of infographics. Another complexity is that are quite dense with a lot of information, and we have several of them with complex aspect ratios like this one, which is very, very long. So the message here is that just an OCR does not work. So for this task, we collected a new dataset called Infographic visual question answering that is composed of 30,000 questions posed on 5,500 images. And some interesting data here is that among other document datasets, our images are the ones that has most text in each image, which means that we have a lot of information that we have to deal with. In addition, the questions are the longest ones. Why this is happening? We think that this is because the complexity of the infographics are such that you need to be very specific on asking something to not be ambiguous. For example, you have to ask about this element in this position about this period time. So you have to be very, very, very precise. But on the other side, the average length is quite small. This is because usually the answers are just one number or 1% or something like that, or a couple of words. As an evaluation metric on this task, we use the average normalized length span and similarity, which at the end is a normalized sum of similarities between the prediction and the correct answers. So as it's easier to understand it with an example, if we have the question of which is the number of the vote and the number is 25,686, the good thing of this metric is that tracks accuracy, but smoothly penalizes the OCR recognition errors. So if the method provides the correct answer, you have 100% of the score, which is 1. But if you only miss one character, like in this case, while the accuracy just gives 0 because it's not the same, we only penalize that unrecognized character. Finally, thanks to this threshold here, if the distance is below this threshold, which is usually 0.5, we assume that it's not an OCR recognition error, but it's a reasoning error. So we set it at 0. The calendar during the competition, we released the first subset of the data on November 10th, so that the different teams could start working on this task. Then on December, we released the full training and validation data, and in February, the test data. And the deadline for the competition submissions was on April. So the different teams had 5 months to work in this data set, and only 2 months with the test set available. we received quite a lot of submissions, 337 submissions from 18 different users, but also only 6 methods finally participated in the competition. We also proposed a couple of baselines. The first one based on the layout LM, which is a language representation that takes into account the word position according to its bounding box. We get the pre-trained weight of the layout LM, keep it pre-training it on infographics visual question answering, and finally fine-tuning. We did some experiments also with the visual features by using bottom-up visual features or using the visual features for the full image. And the visual features we tried with FastRCNN pre-trained on visual genome and MaskRCNN pre-trained on FullNet for document layout analysis. And we found that not using the visual features or using the representation of the full image with the MaskRCNN gave the best results, but with very slight differences, which means again that infographics are something that it's not like generic documents, but also it's not like scene images. We tried another baseline based on the M4C, which is from the syntax world, which consists on an encoder which has a stack of transformer layers that fuses the quest of zero tokens of the image object, and a decoder that iteratively decodes one word at each time step that can be either from the OCR recognition, from the OCR recognized words, or from a fixed vocabulary. We train it on infographics visual question answering. Again, we did different evolutionary studies with different visual features, and in this case, the visual features with full image and FastRCNN were the best. This is the final ranking of the competition, where the Applic AI field method won, and also the ICDAR single model is the runner-up of this competition. Interesting thing is that these two methods are visual and language representations that learns both modalities at the same time, while the following are multimodal extractive question answering methods, and the latest ones are single modality extractive question answering methods. The second task, the document collection visual question answering. Well, first of all, the document consists on the US candidate registration forms. So we have 14,000 documents with more or less the same layout, with just slight changes during the time, but of course filled with different information. So here the task is, we have a question posed over the whole collection, and the task is to come up with the answer to that question, but also with the evidences of these answers. We call evidence the document IDs where the answer can be found. Well, yes, the dataset consists on 14,000 document images, but also we only have 10 questions for that, because we designed it as a kind of retrieval style task, where you have to train your method on another task or dataset, and then use it in the test time for evaluating. Another complexity of the task is that for each question, we have different, what we call relevant documents of each, or different sets of answers. So as you can see, the scale is logarithmic. So for example, for the questions 5 or 6, we have 1 or 2 relevant documents, while for the question 8 or 9, we have up to 200. The evaluation metric on this task is what we call ANLSL, or average normalized length similarity for lists, which it's just an adaptation of the ANLS. What we do is perform an Hungarian matching between the predictions and the ground truth, and get the similarity, the normalized length similarity between these pairs. Then we sum it among all of them and normalize it according to the number of elements. Again, with an example, it's easier to understand. For example, in this question, who are the representative of the Democratic Party? If the answer is Donald McDermott and Gary L. Simpson, if the method provides correctly the both names, but in in different order, it's fine because the order for us is not relevant. But if the method has some OCR recognition error, like as we are using the normalized Lorentz similarity, we only smoothly penalize. And finally, if the method provides more or less elements or answers, even though they are correct, we consider that are not complete. So we also penalize it. In this case, the competition calendar, since the document collection visual question answering task was initially proposed on the previous edition of the competition, the datasets were available from the very beginning. And we had also quite a number of submissions, 60 different submissions from 7 users, from which only 5 methods finally participated. We also proposed a couple of baselines. The first one, text spotted plus verb extractive question answering, in which we extract all the OCR tokens of the documents, we concatenate it, and then from the question, we obtain the most relevant words, but by keeping the noun after using a part of a speech tagger. We compute distance between each of these relevant words to the extracted OCR error, those OCR words, rank it according to these distances, and we run the verb question answering method on the most relevant documents, which are the ones that has a similarity greater than 0.9. The other one is very characteristic. We call it database because we try to simulate how a database works. In this case, we also extract the OCR in the documents, but this time we also extract the relation between the keys and the pairs. So we have the data in this format, like which is the candidate name, and I'm reverse, the telephone number, this one. So we dump all this information in a database like structure, and here we have the main limitation, in which we parse manually the NLP question to a kind of structured query language. Then from this, we obtain both the answer and the relevant document. Notice that this baseline is very ad hoc and cannot generalize at all, but we thought that nevertheless gives a different point of view that it is still interesting. The final ranking on this task is this one, where infrared radar won with the greater ANRSL, but nevertheless realize that the evidences scoring, the previous ones, DQA and DOCR, are still a little bit better than current winner. Finally, the single document visual question answering was not part of this challenge edition, but nevertheless, we think that it's interesting to have a look on the progress during this year, because we have had quite a number of new submissions. In this case, the dataset contains 30,000 questions, worth over 5,000 document images, and the evaluation is also the average normalized Lorentz similarity. This one, that is the oldest one, we have 750 different submissions from 44 users, out of which 28 are already public, and from this one, 21 are new methods after the previous edition. This is the current ranking, where again the Applicate AI, which are the same winners as the Infographics visual question answering winners are. And just to realize, the previous winner was the Ping and VQA in the previous edition. So the improvement is quite noticeable. Just before finishing, I would like to remember everyone that even the competition calendar has been closed, the challenge keeps open, so you can still submit new ideas and new method results. You can find the challenge in the robot reading competition portal, and we have also a project webpage in DocVQA.org. So with this, I leave you with the winners of the different competitions. The first ones will be the Applicate AI team. And also to remember that the certificate winner ceremony will be on the last day of the conference on Friday. Thank you very much.
So I'm next. Can I share my? Am I right? Right?
Yes, thank you.
You can share your screen. Should be working. Wait, we will stop sharing and start. So start sharing your screen.
Okay.
The opportunity for questions will be at the end of the session.
We don't, yeah, at the end of the session.
You got questions on the introduction?
Yes.
Yeah, actually, I have a question.
So,
Yeah, I was just curious about the evaluation metric because you use a soft metric, right? So to not penalize heavily the OCR mistakes, which is quite okay. But I'm just wondering about digits, especially order of magnitude. Because if you make a mistake, like in one digit, especially in some official reports, company reports.
yes.
Ruben, I think David wants to start. You can mute your mic, please.
Sorry?
He is saying that we should.
No, not we. Someone else.
Okay, but
I think you're also not close enough to this.
Ah,
one.
yes,
So if
maybe
you can
that's-
sit on that
Okay,
chair.
okay. And
well, I can repeat the question more than.
okay.
So the question was that we are penalizing the character recognition errors, but it's not the same, especially in digits, if the error is in the last digit of the first digit because of the order of the magnitude. And yes, you are totally correct. We are not penalizing more or less on this. We are focused on characters. Honestly, we didn't think about this. It's an interesting idea, but no, we're not taking into account.
Maybe I can chip in here. The ANLS metric was actually not designed originally for the document VQA. We designed it for the syntax VQA. And there is a big difference there because OCR in real things is really not working very well. So by missing just one character was penalizing basically 0, 1, and that was not meeting next. Then we brought it over to DocVQA. And in parallel, if you see at the competition website, we also report accuracy. So accuracy is not lost; it's just a secondary metric, no. But we thought we'd keep it in because it depends on the kind of task. It might be the case that OCR still doesn't work very well. So in the classic documents, OCR is almost 100% okay. But in the infographics, for example, low resolution, long documents, OCR is actually a big cause of errors. So we needed a way to figure out basically where the error comes from. Is it from the QA system, or is it because the QA system has nothing to work on, right? So it's a chicken and egg problem, and I think the best solution is to keep both columns there, and people can choose what to evaluate on. No, but I think that they serve different purposes. I don't know if that answers the question. Any more questions for the?
Okay, thank you. So whenever you want, you can start.
Okay, so I'm ready now. Hi, I'm David Jurkiewicz, and I will present the winning solution we developed at Applica to the Infographics visual question answering task. Firstly, I will give a quick recap of the Infographics visual question answering challenge. Then I will introduce our text image layout transformer model, which is also known as TILT. And then it will be followed by the details specific to our infographics solution. And in the end, I will show the results. As you heard from Ruben, Infographics VQA is the task of answering questions about visualized data from infographics. And for example, in the picture on the left, to correctly answer the question, one needs to detect the rings forming the Olympic symbol and count them. Okay, let's now have a look at our tilt model. Our work draws from encoder-decoder models, multimodal transformers, and models for text that are able to comprehend spatial relationships between words. Solving difficult tasks like Infographic VQA, where the relative positioning of the text and visual elements matter, it would be hard with a vanilla sequential model operating only on text. That is why our model consumes 3 different modalities of the document, and namely they are the visual features like charts or pictograms, bounding boxes of detected words, or unstructured texts returned by OCR. We based our architecture on the T5 model. In T5 model, instead of using a fixed sinusoidal embedding for each position, as it was in the original transformer, relative position embeddings produce a different learned embedding. And that embedding is computed according to the offset between the key and query being compared in the self-attention mechanism. So similarly to them, we added additional horizontal and vertical bias calculated in the same way as the T5 positional bias, but it is computed according to the distances between the boxes. And moreover, we have extended the token semantics by summing them with image semantics from visual encoder. For every pair of tokens, we calculate its horizontal or vertical distance that falls into one of 32 buckets, which group similarly distanced token pairs. The size of the buckets grow logarithmically, so that greater token pairs are distanced and grouped into larger buckets. So yeah, when the distance is greater, they are grouped into larger buckets. And every bucket is associated with a learnable vector, which in the end is added to the corresponding logit used for computing the attention weights. In the picture, we can see a document with distinguished buckets for the amount token. We decided to rely on the UNet as our backbone visual encoder network, since this architecture provides access not only to the information in the near neighborhood of the token, such as font or style, but also to more distant regions of the page. And this is useful in cases where the text is related to other structures. For example, when the text is a description, when the text is the description of the picture, or when the text is near the checkbox. Yeah. And for each semantic embedding, we add features that are extracted by Roy pooling from UNet's feature map according to the corresponding token bounding box. So it's like cutting the region connected with the token from the feature map of whole document. Yes, and sometimes more than visual features connected with tokens, more important are general features of certain regions of documents, just like it was with the example of that Olympic rings, where the rings mattered, not the tokens. Therefore, apart from adding image features to semantic embeddings, we provide additional dummy images, image tokens, which contain image features for the whole document. Sorry. Yeah, they contain image for the whole document, not only the tokens. And we segment the image into even boxes in such a way that they are always 3 equally sized columns, and the number of rows is calculated by dividing the height of the image by the width of the column and then rounding it up to the nearest integer. And of course, in terms of ultra-wide images, we assure that there is at least 1 row. so that there are at least 3 image tokens. At first, we had a low score, about 30 points in terms of ANLS metric, and many things had important impact on improving the score. So they are ordered by the time how we did them. So we started with the largest possible model we could run, meaning that we initialize our model with T5 large weights, and we pre-trained our model simultaneously in a supervised and unsupervised fashion. And for unsupervised part, we used a large data set of PDF documents from the web. And for the supervised part, we relied on commonly available data sets that are connected with question answering or document understanding, such as SQUAD or DocVQA data sets. The choice of the OCR was one of the key factors. For example, Tesseract OCR performed much worse than Microsoft OCR. The difference was like 10 points of difference. Another important thing was the analysis of the document lengths and image sizes. Since some infographics had very great height and many tokens, it was crucial to consume as much as we could and find a sweet spot between the length of the tokens we could process and the size of the image. So for the tokens, we set the maximum length as 1,666 tokens. And as for the images, it's a little bit more complicated because we scaled every image to the width of 768 pixels, and we preserved the aspect ratio. And then we set the maximum height to be 5,952 pixels. And every image which had more pixels than those almost 6,000 pixels, they were cut there, and the information below, the pixels below, were discarded. Yes, and it also helped like about 10 points. We did a hyperparameter search, and what's improved the score the most was increasing the dropout rate and label smoothing to 0.2 value. It improved our score for about 4 points. And the last thing we did, we crawled many infographics. It was about 230,000. Yes, and we had added them for an unsupervised pre-training that was focused only on the infographics, and it also helped like 4 points in the end. And the results for the Infographics VQA task are as follows. We managed to take a first place, outperforming second placed model by about 23 points. And from what we can see in the table, the hardest answer types were those non-extractive and the ones which required to count something. Yeah. Our model performed very well also on other document intelligence related tasks, and you can find the details in our paper, or you can meet us directly at the first poster session, where we will be to present our tilt and answer any question you may have. So you can meet us directly there. And that's all. Thank you for your attention.
Thank you very much, David. Is there any question or answer? I question about this presentation.
Yeah, I do have a question. Thank you for the wonderful presentation, David. So just wondering that I think in the key point slide that you mentioned, for the last step, you crowd some data for the infographic, right?
Yes.
and you do some unsupervised pre-training on this. Just wondering what kind of unsupervised pre-training you did.
So yeah, it was the usual pre-training, but something like usual mask language model, like the usual mask language model task, but also we added something like that we masked some parts of the image, and the model also would have to reproduce that part. Yeah, and that's all. Nothing special to that.
Okay, all right, thank you.
Yeah.
It's we have a question
no,
here.
it's kind of weird to ask my own team, but actually I have a question about these Olympic rings, right? I'm just wondering whether actually it was just taken from the pre-trained knowledge. I mean, if you have some fake Olympic symbol of, let's say, 7 Olympic rings, whether we would get 5 or 7. I'm just curious about that. Any idea? Is it just the pre-trained knowledge, or is it just looking at actually at the rings?
I'm also curious. It could be the learned knowledge also, so I'm not sure. But there were some infographics we checked by hand when the model counted correctly. Yeah, the things that he needed to count. So not sure how it was with Olympic rings, but with some infographics we answered correctly by counting, I think. Yeah. But the more things to count, the harder it is.
We have another question here.
Thanks for your presentation. I really liked it. I have one curious question. Like, do you have this? Have you open sourced your model weights, like a pre-trained model or code in GitHub? Like, if we can access.
Okay, so we didn't share our weights, that's for sure. If it's for model, the model is still not open sourced, and I'm not sure how it will be in the future. Maybe it will be open source, maybe not. It also depends on yeah.
Okay, thank you for that. And well done. Yeah.
Okay, thank you very much. So I think following the program, we will follow with the next talk, which is the runner-up of the Infographics Visual Question Answering Challenge in the ICDAR team.
Yes.
Okay, so I will stop sharing.
Okay. So feel free to start.
Can you see my screen?
Yes. Oh, but this is
no. That has to be the presenter. Please switch the screen. Yeah, that one.
Okay.
Okay. Now, yes.
Okay.
Correct.
Okay. So let me start now. So hi, my name is Ryota Tanaka from NTT. Today I'm going to talk about IGBART, learning text icon layer representation and arithmetic operations for infographic understanding. This is joint work with Kyosuke Nishida. So infographic is a visual representation of information or data in the form of charts, diagram, and so on. Therefore, infographic understanding requires a model to jointly reason over document layout, visual objects, and text in images. Infographic VQA aims to perform the following task. Given a question and an infographic image, the model generates mod-type answer. The types of the answer fall into 3 types: single span, multi-span, and number. The single span and multi-span answers are sequence of tokens are extracted from images or question. On the other hand, the numerical answer is not a span from an image or question. And in some cases, it requires numerical reasoning between multiple numbers in an image. So to solve this task, we think there are several challenges. The first one is how to obtain better text icon layout representations. The formats of infographics are varied, and our preliminary experiment have shown that it is difficult for a model trained on only the Infographic VQA dataset to obtain enough infographic representation to perform this task. So to address this problem, we collected a large-scale infographics dataset for pre-training and built a new model to run the interactions among text, visual elements, and infographic-related information. So the second challenge is how to enhance the ability of numerical reasoning. Since numbers are present in most infographics, it is important to develop a method for understanding and reasoning about the relationships between these numbers. To this end, we propose a data augmentation for arithmetic operations. Yeah, I will move on the details. So first of all, we collected large-scale image caption pairs for pre-training. The process of data collection has 3 steps: clone, extract, and filter. First, we cloned about 0.6 million infographic web pages that can be accessed publicly. From these cloned web pages, we pass the HTML source to extract image caption pairs. In the filtering stage, we removed the short captions of less than 3 words and images that also exist in validation and test data via URL matching. Eventually, we obtained about 0.5 million pairs. This is the overview of our model. We propose a transform-based multimodal approach called IGVART that can obtain infographic representation for this task. As you can see this figure, the architecture of IGVART is based on multi-layer transformer encoder. Unlike the existing pre-trained models for document layout understanding, IGVART can explicitly run spatial alignments between visual regions and text in images. Next, we define the input embedding of IGVART as the sum of 4 different embeddings. When pre-training, the token embedding is the concatenation of the icon regions, icon tags, OCR words, and caption. In the fine-tuning, the last sequence of the tokens is a question and answer instead of captions. In addition, we use the segment embedding that distinguishes the visual and text modalities. We also made up 1D and 2D portions embedding to consider the 1D token order and the location of the bounding boxes in image. So when training IGVART, following BLP model, we define a self-attention mask that behave like a sequence model to generate multi-type answer. We think that extractive approaches which extract words from start and end positions highly depend on the pre-processing data and limits in span extractions. So therefore, for this task, we believe that the generative approaches are better than the extractive approaches. Similar to BERT, we adopt mask language modeling as a self-supervised task to make the model run better in the language side with cross-modality information during training. So specifically, we randomly mask 50% of input text tokens and ask the model to recover the masked tokens. We develop data augmentation that improve the numerical reasoning ability. Basically, we want the model to understand how ranges numerical answers are calculated. For this example, suppose the question is what total percent of B2B and B2C markets use Google+, and the granted answer is 79%. Actually, the answer comes from 40% plus 39%. Unfortunately, in this task, no annotations are given for the derivation of this equation. So to create this answer, we pre-calculate a combination of numbers in the image and added samples whose calculation result match the granted answer. If the model generated equation like added samples during inference, we performed the numerical operations in the post-processing. This is a setting of our submitted model. For each image, we use first a CNN trained on the Visual 29 dataset to detect icon regions and tags. Specifically, we kept the top 36 object proposal and took the output of the FC6 layer as a feature representation for each region and fine-tune the FC7 layer. To obtain the OCR results from image, we use the Google Vision API. The submitted IGBird was initialized from IGBird large and trained on the training and validation data. Now I would like to move on the experiments. These are the offshore evaluation results. As you can see, our models won second place among 6 teams. Especially on the visual and arithmetic related scores, our model significantly outperformed the third place team. In general, the generating methods, which also used by the first place team, tended to perform better than selective ones. These are the validation results implemented in our experiments. In this setting, different from our submitted models, we use a base size and did leverage the validation data in the fine tuning. This table shows that the pretraining on our large-scale datasets was effective to boost the performance. However, compared with BERT, IGBird without pretraining failed to run. So this indicates that learning the new layer, the icon visual representation on only the Infographic VQA is difficult because the dataset is limited. We also conducted an evaluation study to explore the effectiveness of our data augmentation. In this experiment, we divided the types of granted answers into odd and number using heuristic rules. This result shows that the quality of numerical answers was improved in both BERT and IGBird with our data augmentation. These are 2 examples of correct predictions. The question in the left example is, what is the name of the social media site with a smiley face icon? In the response to this question, our model was able to understand the smiley face icon and the corresponding social media site. The question in the right example requires a method to read and reason over numbers in the image. And IGBird with our data augmentations answered correctly using arithmetic operation. This is a failure case. In this example, the question is what % of all markets have found their customers through Twitter? As you can see, the proposed model could not identify the Twitter icon, which is related to the question, and could not correctly answer its percentage. In order to understand why our model generates the failed result, we further investigate the result of the icon detection. We found that our icon detector misunderstood Twitter icon to be animal. So further research should be conducted on recognizing more varied icon objects without depending on the result from the visual detector. So finally, I'd like to finish by summarizing the main contribution of our study. In this study, we proposed IGBird that can learn icon layer representation and arithmetic operations. We also constructed a new large-scale infographics datasets for pre-training. In the future work, we will further explore the network architecture as well as pre-training strategies. In addition, we will evaluate IGBird in other downstream tasks. That's all. Thank you.
Thank you, Ryota. Is there any question of this presentation? No? Any? Yeah. Yes,
So
sure.
you mentioned at the end of the presentation that you created a new data set. Is this publicly available? Can you describe it a bit?
Unfortunately, due to the license, we are not able to release the corrected data in public, but we will release the only script for collecting the data.
Okay, thank you.
Thank you.
Any other question? If not, we can follow the program and go to the talk of the winner of DocVQA document collection visual question answering task, which is the infrared radar team.
Yeah, sure.
So wait, okay.
Oh, go ahead. Sorry.
Ryota, were you saying something?
Oh, okay. Thank you.
Thank you, Ryota.
Okay.
How long exactly?
Is my screen visible?
Yes.
Okay. All right. Just give me 1 second. All right. Hi, everyone. I'm John Long from the research team of Infer. So today I will present our method on Infer Radar for DocVQA Test 2 competition. So the team members that worked on this competition are me, Deepak, Aditya, and Caesar. So there are 2 major steps to tackle this task on document retrieval step and answer extraction step. So the data are 14,000 PDC documents. Large majority of those documents falls into the same templates, which is very helpful when we do key value pair extraction. So when given a question in human natural language, we need to first retrieve all the relevant documents from the 14,000 documents provided. So this is the searching step. By relevant documents, it means documents that contains the answer to the given question. So after retrieving the relevant documents, step 2 will be extracting all the unique answers from them. So here we present our approach, Infer the Radar, standing for retrieval of answers by document analysis and re-ranking. Here's the high-level architecture for Inferred Radar. There are 4 main modules in our approach: key value pair detection, question parsing, document retrieval, and answer extraction. So first step, we try to populate the database with keys and values through a template-based key value pair detection algorithm. We want a table where we can represent each row as a document, and each row will also contain all the relevant values detected. The keys detected will be used as column names for the table for indexing purpose. We also tried using an in-house key value pair detection algorithm for this module, which uses layout LM plus GCN architecture. However, since our templates are fixed, and document analysis plus template-based key value pair detection yields a better result in this case. Then we have the question parsing module. We're given a question, we had to extract the keywords and the values so we can use them to index from the table created in previous module. Next is the document retrieval module, where fuzzy search algorithm is used along with BERT's model to retrieve the set of relevant documents. And lastly, the answer extraction module, which uses the keywords, the values, and the set of relevant documents to extract the final answer. So let's begin with the template-based key value extraction module. Each of the templates carry a specific signature, which is captured using templates. The overall process will be template detection, followed by generating bounding box location for the desired keys and values. Then we can use them to extract the key value pairs from the OCR data. After extracting the key value pairs, we will use them to populate our database. We also did some post-processing to correct the missing values in the extraction process. So how do we detect the templates and extract the key value pairs? So the documents are scanned, so some of them might be tilted, so we need to correct the orientation. Since the template are fixed, we create some anchor box. We create some anchor box shown in this image, which we create bounding box for the PDC logo on the top left corner, also the candidate registration and the C1 symbol. We use traditional object detection algorithm to locate these three pieces of image in each of the documents. So after correcting the orientation, we predefine a set of bounding box to capture the desired key values. The predefined bounding box location are shown in the right image. So after defining the bounding box location for each key value pairs, it's easy to get the key value pairs from the OCR data with some bounding box matching. So next up is the question parsing module, which we use many spacey library in this module. First, we generate a list of generally occurring words in the question. For example, for words like which representative or who in the question, probably indicates that you're looking for the keyword candidate name. We also use spacey to identify subjects, verb, and objects. And lastly, we use NER to extract the name entities such as person, organization, and date. All these information would then be concatenated into a query where we can use them to search in the database that we created. So here's an example of how the question parser works. Given the question, which candidate from the Libertarian, Independent, or Green Party ran for the election in Seattle? The generally occurring word will be which candidate. This will be mapped to the keyword candidate name, which will be the key for the answer that we need to extract from the database. Then spacey will extract objects like Libertarian, Independent, and Green parties. Lastly, the NER will extract the location Seattle. Then this information will merge into a query shown in the bottom part of the slide, which is select candidate name where party is Libertarian, Independent, Green, where county is Seattle. So moving on to the document retrieval module. There are two steps in this module, fuzzy search step and the re-ranking step. So for the fuzzy search step, we use keywords and values from the question parser, along with the fuzzy search algorithm. We can retrieve our initial set of documents. This retrieval algorithm is completely keyword based. So how does fuzzy search algorithm works? Once we get the keywords and values from the question parser, we can use them to index from the table. So let's go over an example. Let's say key one is the keyword we got from the question parser. Then we can look through all the 14,000 documents to see if the value matches the keyword from the question. Let's say key two is another keyword. Then we do another search through the list of documents that has previously matched the key one. The row which contains match for all the keys will be identified as relevant document. In this case, it will be row 2 with document ID 00001. So since we are dealing with both handwritten and typed documents, our OCR will not be perfect on some of those documents. So we need a way to score the similarity between the value and the question parser. Fuzzy search algorithm does this by using Levinston distance, which is edit distance between two pieces of text. So if two pieces of text is similar, then the Levinston distance will be lower. We set a threshold for the Levinston distance, which is 0.5. And if the Levinston distance of two pieces of text is smaller than the threshold, then we consider it as a match. So after we get the initial set of documents from the fuzzy search algorithm, next step is to re-rank them using BERT large model. So since there are only a few questions provided in the sample set, we decided to use BERT re-ranking model that's fine-tuned on Microsoft MS macro dataset. We further fine-tuned the model checkpoint on in-house question document pair datasets. The final re-ranking model is used as a binary classifier to output relevant score given a question and a document. So if the ranking model gives a negative score for the document, then the document will be removed from the initial set. By using both keyword-based algorithm and the re-ranking algorithm, we are able to reach better retrieval result compared to just using one of them. So finally is the answer extraction module. So given the relevant document from the document retrieval module and the keywords values from the question parsing module, we can easily do a lookup in our database to extract the answer. So for example, if document 1 is relevant from the document retrieval module, then and the key P30 is the key for the answer, then we just index to retrieve to extract the final answer. So that's all for our approach in Infer the radar. Our method scores 0.77 for ANLSL for answer extraction and 74.66 MAP for document retrieval. Yeah, that's it for me. Thank you.
Thank you. Thank you very much, Young Long. Is there any question? Yes, we have a question here.
You mentioned something like Microsoft form dataset or model. Could you go back to the slide?
Yep. Sorry. Oh no, it's here.
Yeah. So what's this? This macro dataset?
Mm-hmm. Yep.
Could you say a few words about this dataset?
Oh yeah, so we use the model checkpoint that's trained on this Microsoft MS macro dataset, and then we further fine-tune with some in-house document question pair dataset.
But what is the dataset about exactly?
This one, the Microsoft dataset.
Yes.
So, it consists of, I believe, 400 million query and passage pairs. So, but the model is previously trained on the 400 million pairs, and so basically it consists of a query and a passage, and the objective is to either output if that query is relevant to the passage given.
Okay. Thank you.
No problem.
Is there another question in the virtual platform? Okay, so then following the program, if Brian, are you ready? Oh, okay. Thanks. Faisal?
Hey.
Hi. Okay, so we can continue.
Thank you. Let me welcome Brian. Brian Price is a senior research scientist in Adobe Research. His research interests encompass computer vision, graphics, and machine learning, with a specific focus on selection and segmentation in terms of interactive and automatic image and video binary matching, document understanding, and image synthesis. Brian has developed technologies that have gone into many Adobe products, including the object selection tool and select and mask tool in Photoshop, the smart selection and auto select tools in Photoshop Mix, and the refine edge and key cleaner features in After Effects. Recently, Brian has worked with the Acrobat team on document-related technologies. He has received his PhD degree in computer science from Brigham Young University in 2010. So we look forward to a lot of interesting work that Brian has done, how he's put that all for us to give a talk on understanding data visualizations via question answering. So looking forward to a very interesting task on how these technologies are used to understand bar charts and pie charts and how we can do VQA on them. Over to Brian.
All right, thank you. Let me get my screen to share here. So you guys can see my screen, right? I'll assume you can.
Yeah.
All right. Thank you for the invite. Why is my screen not going into presenter mode? There it goes. Okay. Thank you for the invite and the introduction. So as you guys are, I'm sure, aware, documents can be pretty complicated. There's a lot of elements that can be in them, you know, charts and images and tables in addition to the text. And, you know, here at Adobe, we have Acrobat with PDFs. And so, you know, there's a whole world of PDFs, all very different, lots of those. Documents are generally created for communicating information, and often will be, you know, may have certain types of information very densely in there. And, you know, if we want to be able to help our users, you know, at least for on the Acrobat side, it would be great to be able to go in and answer questions in these documents. And those questions may need to refer to many types of visualizations. And because of this, you know, a few years back, we started looking into how we can do this. In particular, I wanted to tell a little bit of a story of how we started working on understanding data visualizations. And to start off, you know, this was kind of before most people had really tried this. We were starting something kind of new. And so we started looking initially just at bar charts. We started with building a data set, and eventually through a couple algorithms I'll explain, we were able to essentially solve those data sets and get superhuman performance. And so I'm going to kind of talk through that story of how we did that, and then, you know, also point out what could be coming next. So this is work I did mostly with a former intern, Kushal, who actually is now here at Adobe, and my longtime collaborator, Scott Cohen, here at Adobe. And then also Chris was Kushal's professor at the time. So before we really looked at trying to do question answering on documents and on charts specifically, you know, there was a lot of work and working on images, and they are very different tasks. You know, if you want to answer questions about natural images, they're often very diverse. There's lots of different types of things that can be going on. The questions are often diverse, written by humans. But the interesting thing is it's not always clear where the information is going to come from to answer the question. There can be a lot of different correlations. So, for example, if you were to ask, is this sunny? You know, if you were to look at this image and say, is it sunny? How would you determine that? Maybe it's the overall brightness. Maybe it's the hard shadows, and there's a lot of hard shadows. You know, there's a lot of information kind of spread out around the image that you can look at to figure out, is this sunny or not? On the other hand, if you have a chart and you ask a question about this, it's more specific. You need a long chain of reasoning to get it. So, you know, with this question, what is the value of claim in plenty? You know, you'd have to figure out what claim is. It's this blue thing, and then you have to find plenty. It's over here, and you need to find the bar, and you need to measure it. There's a very specific chain of reasoning you need to follow. And you may notice these are kind of nonsense words here. For our data set where we generated these automatically, we didn't really care what the labels were, so we just used random words because the OCR engine, you know, the algorithm wouldn't necessarily understand that. But, you know, to continue, you know, if you really want to handle this correctly, we need to have OCR integration and be able to handle out of vocabulary answers, so things that we didn't see in training. And again, you know, like I said before, these we're really trying to communicate specific information. That's what these bar charts are doing. They have a lot of specific information in there. And so we want to be able to pull that meaning out. So to our knowledge, we were the first group to be trying to solve these type of problems. And I want to point out, at least at the time, doing this is very difficult. And so if we, for a human, they'd get about 88% on our data set, while the best state-of-the-art image VQA problem would only get about 36%. It couldn't handle things like out of vocabulary answers and OCR, and it struggled. So, we had two papers. I'll go over each of them. The first one is published in CVPR 2018, DVQA, Understanding Data Visualization Using Question Answering. So first, let me talk about the data set. So we needed a data set. We synthesized a bunch of images. We had about 300,000 in total. And we did try to make sure we had a lot of different variation in appearance. And so they'd be horizontal versus vertical. We'd have kind of these stacked bar charts versus grouped bar charts. We try to add in a lot of differences there. And we also wanted it bias-free. So for, it's been found that for, image VQA, if there's a yes or no question, usually the answer is yes. We wanted to try to avoid that by getting rid of the bias like that. And then we also needed a lot of questions, and we also synthesized we generated these automatically based on some templates, and we had three basic types of questions we were asking. The first was structure understanding. This is just basically understanding the structure of the table, like how many groups are there or how many bars are there? Are they horizontal versus vertical? So things like that. Then we got into the data retrieval, and these are a bunch of examples here you can read as I talk here, but for data retrieval, it's more like, you need to look in one area and figure out what that is. So maybe it's the height of a bar or which color corresponds to a particular word. And then we had reasoning. Reasoning would generally require you looking in multiple places and needing to accumulate information across the chart. So it may be something like, summing all of the categories across the chart, or seeing, comparing which is the highest of two specific categories. Things like that. So now that we have this, this data set that we generated, we had two methods we actually proposed in this paper. So I'll go over them both quickly. This first one, we called it MOM, multi-output model. The idea is that we had the bar chart, which you see here, which would feed into a model, and then we'd have the question, which would go into an LSTM. So the top model is the CNN. And then from there, we actually had two specific networks that would handle different types of questions. So for this top one that you see in blue, hopefully you can see my mouse as I'm pointing to it. This would handle questions like the blue question over here. Does the chart contain stacked bars? So that is a yes or no question. So we know what the output would be. And so this top branch was handling questions where we knew what the output would be. Maybe it's yes or no. Maybe it's a color that corresponds to one of the colors in the chart, or maybe it's a number that corresponds to one of these answers. And so it's something where you can just list out, here's all the possible answers. And so these features would essentially just go into a neural network that which was a classifier that would spit out an answer. The second network was to handle questions that required actually reading something in the chart. So in this case, which algorithm has the lowest accuracy for any data set? You need to figure that out, but then you need to actually output one of the written words on this chart. And again, we wanted to handle out of vocabulary information, so things that weren't seen in the training set. And so we had the second neural network, and what it actually would produce, if you notice here, there's a box, V-box prediction. We would actually output a bounding box. It would try to figure out the location of that word and output the bounding box. And then from there, we would take that bounding box and just feed it into an OCR engine. And we would produce the output. Now that was the first model. We had a second model, which was Sandy, and this was based on at the time, the state-of-the-art image VQA problem. What this was doing, and I'll just jump into what this was doing here. Assuming that we have a chart, which you see here, it's going to go into a model, and then we need to output an answer. And once again, we had two kind of questions. The top question here is where you require reading something in the chart, and then the bottom question is just like a yes or no or something that had an output. What we did is, as a pre-process, we would go through and detect all the text and read the text, and then essentially assign it to a token. So the word gift is assigned to the token 0, and edge is 1. And this was a dynamic process. So we had this dynamic encoding, where each of these words was encoded to a token, and then those tokens would just be added to the list of possible answers. So you'd have some tokens that corresponded to the chart specific words, and then you'd have the static ones that were, yes or no, and colors and numbers and things. And then the neural network that way would just read through it and treat this more like just regular classification. And so let me show you the results that we got on this. So we had a number of baselines we compared to. One was the yes network. They would just always answer yes. So this is just handling the bias of yes or no questions. We had one that used a CNN only on images, and one that used an LSTM only on questions. So these should be able to handle, again, any bias in the data set where there's certain answers or certain images that always have the same output. And then we combined the two of these for a very simple baseline. And then we also compared it to the image VQA state of the art. And we had two different test sets we actually did. The test familiar, which is all the labels that were in the tables, were seen in the training set. And then we had the test novel where none of them were. So that was really testing out of vocabulary answers. So here's a chart. Let me just walk you through this real quickly. So you can see we have two different sets of data here, the test familiar and the test novel. And we get the results on each of these three types of questions, the structure, data, and reasoning, as well as the overall. And if we just look at the overall here, you can see our yes or no. If you just always answer yes, apparently probably about 20% of the questions were yes and no. And so it was able to get about 11. You can see it kind of maxes out on the previous state of the art at 36. Our mom model was able to get up to 45. If we used Oracle OCR, we could get 56%. If we used our trained OCR, it's only 45. So there wasn't a big difference between mom and Sandy if you didn't use Oracle OCR, at least on the data set where all of the labels were in the training data. If you look at the out of vocabulary experiment, there's a bigger gap between our two methods. We're only 40% for mom and 45 for Sandy. And with Oracle OCR, we could get up to 56. We also showed specifically what results we would get when you had to read a word that was written in the chart. And so we had for chart specific questions where one of the words in the chart was in the question, and then the chart specific answers is where the answer is one of the words in the chart. You can see that our baselines could not perform at all on these chart specific answers. They just didn't have OCR. They couldn't read what's in there. So they performed very poorly. And we're able to do quite well. Again, 52% if we had Oracle OCR, but there, at least with our OCR, there's quite a gap here between, I guess if we look at the overall between the 45 and the 56, we could get there. To show a couple examples of what the output was like. So this chart here, this is one of the test images. It asks how many objects were preferred by less than 7 people in at least one category. And so, this will require finding, where 7 is, seeing what hits it, then looking at categories, counting them up. All the models were able to figure out 2. It's hard to know whether they figured out this is asking for an answer and they just guessed, or a number and just guessed a number, or if they really figured out all the reasoning. However, one like this, which category does the medium purple color represent? This does require reading, so we know that it's going and trying to read it. The image VQA answered closet, which is not in here as an answer. Mom had licit, which is actually the correct answer, but bad OCR for list. And then Sandy got list. Another example here, which item sold the most number of units summed across all stores. So this would need to do some summing. And both our methods are able to figure out the right answer. And then, how many units of each item were sold by the store sister, where you have to look up sister and, go look that up. And both, all these methods could get that. So the takeaway from this first paper is, we did have a big improvement over the state of the art if you just applied image methods to it, but there's still a huge gap between what we could do and what humans could do. So we then had, a couple of years later, we had another paper where we looked to bridge this gap. This is our answering questions about data visualizations using efficient bimodal fusion. We use a method called prefill, and this would create these bimodal embeddings using higher and low level features in order to answer the question. And I will show what I mean by that. And we were able to get superhuman performance, at least on our data set for this, given that we had Oracle OCR. So I mentioned before the data set we had DocVQA. At the same time that this came out, there was another Figure QA data set that came out. And so we wanted to look at addressing both of these data sets in this paper. I do want to point out the differences. So they're fairly similar in size, of number of images and questions, a little bit more for our data set. The big advantage of the Figure QA is it actually had 5 different types of charts. So it had pie charts and line charts and a couple others in addition to the bar charts. Well, we only had bar charts. However, all questions of Figure A were yes or no, while we had open-ended questions. And they didn't require any OCR or out of vocabulary understanding, which we required. And we actually had more templates, and so we'd have a lot more variations in our bar charts than they would have. And they had 15 essentially templates over the 5 different charts, while we had 26 over just the one. So that's the difference, and we wanted to look at tackling both of these. And so for our prefill method, the way that it would work, here's kind of the whole model. And there's 3 kind of key ideas. Let me go over each of these. So the first one is that we had this, we would pull both low level and high level features. And so we have the chart, which you see here, which would go through some convolution. And then we would have a question that would go through an LSTM. And after the convolutions, we have these dense blocks, which you see kind of depicted over on the right, which were gathering up features. There's a number of transition layers between each dense block, but you see we pulled some of the visual features kind of early on. So these should have low level features, hopefully corresponding to things like texture and color and such. And then we have a lot more convolutions happening before we pull some additional high level features. So we're going to combine these low and high level features. The second thing is, and this is all embedded kind of in this little block here, for each of the features, visual features, we're going to append to that or concatenate to that the word features. And so each of these bars represents one visual feature and all of the question features. And so this is kind of an early fusion. We're going to fuse up these features early on and then run them through a number of convolutions. This allows us to build, like we said, this kind of bimodal embedding, trying to put the questions and the visual features into a common feature space. And then what happens here is that, once we go through a number of convolutions, now we have some new features. That's all these red blocks. And instead of just doing something like pooling to aggregate these, what we actually do is we do this recurrent aggregation. So we have this bidirectional GRU that we go, pass through these and use this to combine them. And we found that this does a much better job of bringing together this information. And then once this is done, we then feed it into this classifier. So now we have this, this bimodal embedding that we had of these low and high level features that we combined with this new, recurrent way and fed this into this classifier, combine the low and high level features, and that will give us the final answer. So that's the basic idea of what the model was doing here. Now to look at the results, we can see we had, we looked at question only. If we only feed it the question without any image, and for DocVQA we don't do that well. For Figure QA you can get 50% because all the questions are yes or no, and so you have a 50-50 chance. And then we marked the prior state of the art on each of these 2 methods, and then our human performance in red, and then our method in green. And you can see we are actually, well, first you can see we have a huge improvement over the state of the art, 37% on DVQ and 21% on figure QA. But we actually are outperforming humans on this data set, which we were surprised. It was kind of shocking. We weren't expecting to do this well. In fact, the reviewers were kind of upset that we did so well on this paper. They asked, question, that they suggested this is too easy of a data set, which it hadn't been until we came up with the solution. So looking a little more specifically into the answers, again, we divided this up between so this is the DVQA question results, and then I'll show the figure QA afterward. So we have the same breakdowns of the, out of vocabulary or knots, as well as the different question types. Just looking maybe over here on the far right on the out of vocabulary ones for the overall, you can see we had a couple of baselines like just the question or a simple baseline that got to about 32%. If we look at our methods without OCR, we can get up to 47%, so we can't quite answer any questions where we need OCR for. If you look at our prior state of the art we use Tesseract OCR, we were able to get 45% with our old paper, Sandy. With our new algorithm prefill, we got up to 69%, which is a lot better. We then trained our own OCR, which we got up to 80%. And then if we were to instead use Oracle OCR, we'd get up to 96%. So you can see if we use our OCR, we're actually not superhuman. It requires the Oracle OCR. But still, we're able to make a huge improvement from the old state of the art, kind of down to 45% up to 80%. And now looking at figure QA, and so they had essentially 15 templated questions, and you can see the results for each of these. So we have the prior state of the art, and then the human performance in hours. And in bold, you can see that we not only outperformed humans and the prior state of the art overall, but almost on every single question type, we could outperform people and the prior state of the art. And remember, these were yes or no questions. And so, yeah, we didn't need to have any out of vocabulary answers. We didn't have any OCR going on. So we're pretty excited about these results. One other thing we showed in the paper is that we could actually use our question answering to extract out a table of the answers. And we would just use this by first asking structural questions like, how many bar charts are, how many bars are there? How many groups are there groups? Things like that. And that would give us the overall structure. And then once we have the structure, then for each cell, we would just ask the appropriate question of what the values were to go and get that. And this is an actual result we had where we got everything right except for the paper answer in the noise category, we got 5. And if you look here, that's this blue bar, it should have been 6. So the takeaway from this, we basically solved the DVQA and figure QA data sets. That doesn't mean we solved the question answering problem for all, but completely, but it means that those data sets were simple enough we were able to solve those with our machine learning. We were excited about that. It did leave the question of what next? What should we continue working on? So we have a few suggestions for this, and these may complement what people are doing right now for the stuff that we're working on with the DocVQA challenge. But one is we really need charts in the wild. And so for our charts, there are all these templated charts, and there is a big jump between having these templated charts like in our 2 data sets and real images. We're not sure that our kind of dynamic encoding, for example, will work for general charts. We haven't tried that. And so that would, having a large data set of actual charts that people made would be a huge improvement there. Another one is to have human generated questions. Again, with our example, all of the questions were templated, and that gave some structure to the questions that really helped out at least the language part of our model to be able to understand and figure out what it's looking for. While we would want to tie it closer to what humans are asking, they'll ask in much more free-form way and may even use synonyms for certain words. There could be a lot of, it'll become much more difficult once we do that. The other thing is that, would be interesting to more explicitly model the cognitive processes that are going on to answer these questions. So, you know, if you remember at the beginning, I pointed out that if you want to answer certain questions, you need to look up one or two values and kind of go along them and compare sizes and things like that. And we think that, at least to some degree, must be implicitly happening. I mean, we've got really good results. So implicitly, it must be figuring out how to do this. But to more explicitly model this may allow it to be able to extend to more real world questions and be able to do a much better job there. And, you know, so doing that instead of having this be black box. And then, you know, pushing beyond this, you know, we'd love to see more work, and we're excited about, you know, this VQA challenge, the document VQA, but, you know, trying to extend this to real end-to-end document understanding. And so if you have a document or a huge set of documents and you have a question there, it's quite possible that you will need to you know, you might need to read a chart, or you might need to look at a table or read the text, or you may actually need to, you know, consult both the, you know, the text and a chart. You know, it's possible that you'll need to look at many different places in this document to really answer these questions. They may even be questions of something in an image. So now you need image VQA coming into this. And then, of course, if you have a large set of documents, you would need to go through all of those, as you guys are aware. And so being able to do this in general on general documents would be very difficult. You know, I would love to, in one day, you know, in something like Acrobat, instead of having the little, you know, you do a search and you search for a word and it just finds that word. It'd be more interesting if you could type in a question and have it go through your document or set of documents and find answers and point you to them. But, you know, there's still a long way to getting that work on the huge, wide variety of types of data that exist in, you know, PDFs, for example. But that is something that we're excited about, being able to look into these, you know, documents, understand them at a much deeper level to be able to do things like question answering. And that is my talk. Thank you.
Thank you so much, Brian, for the very interesting talk. And I'm sure there will be a lot of questions. So I'll break the ice with a simple question. Where do you think, in terms of Turing test for AI, is this in this narrow domain for bar charts and pie charts question answering we stand? Do you think we are really there where Turing test would pass for this problem?
That's a good question. I mean, I don't think with our current method that we are there yet. I mean, I guess we are on these simple types of charts that we did because we beat humans. And so that's pretty good. Like I said, once you use the non-templated questions, I think we'll see a drop there. And we are using Oracle OCR as well. So I don't think we're quite there. I do think that, you know, for something just like the charts, there is a lot of structure in there. I mean, they are specifically structured so that humans will be able to quickly digest and understand the information. So it makes sense that we should have, you know, be able to develop methods that can kind of do that and compete with humans. And I hope to see that on, you know, more general charts in the not too distant future. Going into general document VQA, though, that's a much harder problem because that really that is almost like a machine learning complete type of problem. I think you need to understand all of the text, and you may need to understand, you know, the human understanding of the world, the way people answer questions. And if there's images, you need to understand the images. I mean, there's just so much there to really solve the problem that would need to be done.
Thank you so much. So there's one question from the audience. They are a bit skeptical about the human performance. Why is it so low? It was like 88%, I believe, on average on your experiment. So could you kindly explain what could be the possible reason, or what was the study design for the human part of the experiment?
Yeah, so we took our whole test set. At least I'm pretty sure we took the whole test set. I guess we would have had to for these results. And we sent it on Mechanical Turk, and we had people answer the questions. And I think it is partially, part of it might be that, you know, Mechanical Turkers are trying to optimize speed over right answers so they can, you know, make their pennies per chart. And so that could be part of it, is people just moving quickly. The other part is that some people may just struggle with things like reading charts and, you know, looking at and comparing different things. Having little kids, I know that, you know, there is a particular grade at which they test this, and so hopefully adults would have at least that level of understanding. I would think if this was more like a test in school and your grade depended on it, that people probably would be able to do better. But at least that's what we found on our, you know, in the way that we did it on Mechanical Turk, that's the result that we got.
Awesome. So there's another question from the audience about what would be the impact of if we want to do that on multiple languages. Let's say there's a document question from Europe coming from different European languages. So let's assume there's an Oracle OCR, so that is not a challenge. So what do you think from the NLP or LSTM perspective would change if we had multiple languages, or we had to deal with multiple languages?
Yeah, so that's a great question. So I think with our specific problems that we handled, we would need to train a new language model to understand the question, because that would be in a different language, presumably. And so that whole, you know, in all of these models that have some network that's reading, you know, this section here, this isn't the best example, but we would need to retrain that. As far as the rest of it, you know, we were trying to, you know, in this example, we're doing detection essentially, and then having the OCR go and read that. So as long as, you know, our detector will work, which may or may not, depending on how different the script is, you know, as long as we have the OCR that's trained for that language, it would work well. I think for our cases, it would handle it pretty well, just retraining it for the different languages. You know, prefill as well, you know, you would need to retrain the LSTM. I don't know that there'd be a huge difference after the fact. That would be interesting. So I think the fall off would be essentially how well the LSTM worked and how well it did. Because, you know, other languages will also have different things, you know, very different grammars and things like that, which wouldn't affect the chart too much, because usually those are just simple labels. They're only a word or two. So as long as you can read those words, I think it would be okay. But you would need to retrain this for every language you wanted to handle, at least, you know, to be able to handle the question part.
All right. So thank you so much for such interesting talk. There are more questions, but I'm afraid we are short of time. It's only 14 minutes coffee break, to be precise. So thank you, Brian, for the lovely talk. And for all the on-site participants, enjoy the coffee.
Yes, unfortunately, there's only a short coffee break now, 15 minutes.
Thank you, Faisal. There are actually about 20 people in the room as well. I don't think there is any questions for Brian, no? So we can relieve the speaker. Okay, thank you very much, Brian and Faisal. We'll do a short break, you said?
Yes, coffee is upstairs. So 15 minutes is really just 5 minutes up, grab your coffee and come down again.
All right, thanks. Bye.
It's a pity you don't have a visual from the room.
Those being online, please stay online. Don't leave. And I will make record rooms. 3 breakout rooms, and you can choose by yourself which breakout room you want to join if you want to discuss with some people online. So there are now 3 breakout rooms open. You can just join the breakout room and discuss with people online. You can see also in the room list who is in which breakout room if you want to.
So we join with this one camera, and then the rest can join on the wall. Okay.
Otherwise, it's like because the company yeah. That's it. The most important thing is the because this is a starting point. I mean, if you don't have because if you get an improvement of 10 points, that means that it's yeah, it is one of the most important things. Yeah,
Let me explain my
really worried that I think that the doctor I from them. I used it when I was working there, and maybe I forgot that. I think someone else usually I don't. So I have to wait for everything
Dimos? Can you hear me? Or
Because it's this one which I was using. This I was using this one. I guess.
excuse me, the invited speaker, Amanpreet Singh, is on site or online? Anyone knows? Yep. Who are you now? Now, who is speaking? I cannot see your face.
I don't know what is the camera. No, but now everybody's in the coffee break, so nobody's in.
Yeah. Is it Joseph?
Yes.
Oh yeah. Yeah. Actually, I'm seeking for invited speaker, but I cannot find his name on the online account. The organizers, can you hear me?
Yes, we can hear you.
Yes, unfortunately, I cannot find the next guest speaker.
What's the name? Sorry.
Amanpreet Singh.
Yeah, I have him coming in. You know, there are some people like Anonymous trying to join. And I'm them in the chat that they have to use their proper names. But Amanpreet is there.
Where? Oh, yes. Now I find. Thank you.
Hi.
Yeah. Thank you for joining.
Can you hear me?
Yes, yes, yes. I'm chairperson of this session. So it's nice to see you.
Meet you.
Yeah.
Let me try sharing my screen.
Yes, please.
We also have a person, Yi Yuan Lu, who is always trying to join, but we don't have that person in the registration list.
So I still cannot see your slide.
Yeah, I'm actually giving it permissions.
Mm-hmm.
Give me a second. I need to reopen it because it can't record until I.
The Amanpreet thing from Facebook. So as you know, the Amanpreet is the expert of the adversarial VQA and text VQA and famous text caps, etc. And he also proposed the super glue, yeah, for a new metric of NLP. So today, he will give a talk titled "Towards Models That Can Read and Reason About Syntax." Yeah, so please welcome Amanpreet.
Hi, thank you for such a nice intro. So yeah, I think I'm Amanpreet and I'm actually a researcher at Facebook AI Research. So today I'm actually going to talk about our journey towards the models that can read and reason about seen text in general. Yeah, so for the outline, we will specifically be talking about text VQA dataset and text caps dataset, and then we will discuss the challenges in seen text reasoning and the current approaches and how they solve them, and finally a text OCR dataset, which is a recently released dataset. Yeah, so let's jump into the motivation of like why exactly we built all this ecosystem around seen text, including the organizers of this workshop. So if you see the first example, like it asks what is the denomination of these fields. And when we were creating these data sets, the VQA SOTA would use to answer 50 without any reason or like reading the text inside the image. Similarly, this example is very simple. If you can read the text like which direction is shown, the VQA SOTA will randomly answer east based on its bias. Then similarly, like what is the title of this magazine, then the VQA SOTA will answer not sure because it just can't read text. And in the final example, like there's so many P's on the row, but like the VQA SOTA would answer there are no P's. So similarly in the other state, like if like for blind users or like the sight blinded users, like if we ask a model to like caption an image for their purposes, if it contains text, human will usually give a caption that contains text so that the image has some meaning or sense in it. But the SOTA image captioning model before these data sets would answer something like a white font sitting on the top of the table, which doesn't really give you any context or like clarification about what exactly is in the image. There are other examples like which basically show that these models really can't read text in any sense. So this basically led us to like understand that there is no sense of like reading or reasoning about text in the images in the current reasoning models. So the first question that came into mind is like, why exactly this is happening? Like, is it due to less data, which would be the more obvious case, like if the data in the current data sets is not enough to like learn these capabilities automatically. So we checked around the current data sets and in VQA 2.0 and COCO, which were like standard training data sets for VQA as well as captioning. So the questions don't really like focus on text in any sense. So even in any other case, like only 35% of the images contain text inside COCO dataset. And even further, like only 1.4% of these questions have answers as one of the OCR tokens that were detected there. So you can see on the side, like even the captions don't really are concerned about the text inside the image. There was another data set at that time that has actually grown a lot since this scene text field has started like towards reasoning. That was WizWiz, that is like targeted towards like sight disabled users. So they also contain captions as well as like the questions around these images, but they only 14% of the images actually contain text. And even in those, like 3.2% of the questions have answers as one of the OCR tokens that are present beside the images. Even further among those, 58% of the questions are unanswerable, which really doesn't leave enough room to learn about scene text. So this lead to like actually us like creating DocVQA to complete a gap in this space. We specifically asked the annotators to like create questions that require reading text inside the images. So we first filtered out like 28K images from open images, which actually contain text. This led to like 45K questions, which actually have 10 answers per question, similar to VQA dataset. We also, following the gap, like we actually created the captioning dataset, text caps as well, which is collected on same images, and it has 140K plus captions that actually require reading text in the image to answer. So these are all the examples from DocVQA and text caps dataset. So you can see these capture like text in some sense, so the image with the text has some context and some meaning for the user who is actually reading or like getting the caption from somewhere. So this solves one problem, like DocVQA and text caps, like the less data like that. Now we have some data to train upon. But the other question that actually happens is like, are the current models competent enough to even use this data set? So we actually trained the state-of-the-art models on DocVQA and see that the performance still didn't improve a lot. Like from 10% to we jump to like 13%, only 3%, which is like still a big gap from the human accuracy on these data set, which is 85%. So that led us to believe that even in these models, there is like some issue that we haven't even fixed, that is not related to like having the data or not. Similarly, on text caps, the current captioning state-of-the-art models weren't able to perform really highly compared to the humans on this particular data set. So we realized that these current models actually lack architecture capability to do captioning or answering about questions inside the text, which was like a bigger issue compared to having data in that sense. So let's actually figure out some challenges that are there inside these data sets, or like in general scene text reasoning. The first major issue was like open-ended vocabulary. So text in the image can really be anything. So you can't really comprehend inside the fixed vocabulary and say, okay, I will predict text as it is. So like in this case, even like if you had to like predict the times in the day, right, you will have 14 under 40 combinations just on the time itself. So this text literally can be anything. So this open-ended vocabulary causes issues in when you're doing predictions or understanding words about it. Like generally in like QA systems, like you have a fixed vocabulary from where you predict. So this was not applicable in this case. And then another aspect is like, even once, if you, let's say you solve a vocabulary problem, you have multi-word predictions to like do like even for captioning and like mixing them with like normal vocabulary, and then also predicting multiple words and then understanding which OCR text goes which OCR text. For example, in this particular example, if you have to answer who wrote this box, you have to figure out that these three words are together as an author's name. There's also another open problem here. Then even at the root of the problem, like text detection in itself was a very hard problem for us. Like in this example, particularly the OCR system wouldn't detect any of the actual dates or like the times inside the watch. So even if you detect the text, extraction is also an issue. Like here, like Crayola wasn't like, actually was detected, but they couldn't extract it out because it was reversed in that sense. So there were like a lot of issues that were happening. And further, like these require very advanced reasoning. Like in this particular example, you have to count the number of pencils and then join them together. Excuse me. And finally, like word knowledge is always a prerequisite for these models. Like figuring out that the L is like a little bit occluded, so you have to figure out that Intel would be the brand name here. Finally, for captioning, you have to create coherent captions while figuring out how like OCR words go with the normal vocabulary. So there are a lot of issues that need to be figured out in this particular aspect of syntax reasoning. So let's talk about the approaches that have like come out since this released these data sets and how they tackle some of these issues in some sense. So LoRa was the model that we originally released with the DocVQA paper, like solving at least some sort of issues, like some of these challenges in some sense. But we have come a long way since then. So specifically for the open-end vocabulary, we introduced a copy module that will actually allow you to copy OCR text directly into the answer of the question. So that actually led us to like increase the text accuracy on DocVQA to 28%. So there was like still a huge gap to go from here to like 83%. So we're still not there, but like this was still some progress from 13% to 28%. So the field matured, a lot of other data sets, including from DocVQA workshops, organizer like came out on the similar concepts. And like next year we'll release a transformer based model, given that the transformers were on fire like everywhere. So this model was like much better than the previous model that LoRa that we released. This actually increased the text accuracies to 40.46%. At this point, we also had like text caps. So the side and cross on text cap also like started increasing. So this actually handles multi-word predictions really well because it's a generator model. So including multi-word predictions like actually helped increase the performance a lot on the data set, on the DocVQA data set, as well as text caps. So at this point, like the same model can work on text caps because it's multi-word prediction as well as on DocVQA, depending on where you train it. So we also improved OCR systems with the time, and like they also led to like huge improvement along the time. And the next talk is on this particular model. And this now introduced pre-training into the picture. Like you can basically pre-train on large amount of OCR data that you have, and then finally fine-tune it. And given like the word topology and everything, so you can do MLM and other kind of pre-trained tasks to like improve performance. So this further increased performance to like 54%. So, and the text caps side jumped to like 104. So we have been seeing consistent improvement over time. So pre-training also helps you like understand better priors around the data sets. And the current state is like so we have been running DocVQA challenge for 3 years now. So in the third year, we have seen like one model achieve actually 74% on the data sets. So the gap is still there, but the gap is very narrow now. Like we have been seeing consistent improvements over time with larger and larger pre-training happening in these models. So on the other end, like I think there is still like a base issue of like that text in itself can't be properly detected. Like over the time, we realized that that the OCR was like a main issue in like improving performance on these data sets, and there weren't like any good scene text, real images scene text data sets available in the OCR field. So this was a good opportunity to like basically focus on this problem inside the OCR field. Like if we can get a really large OCR data set to train these systems really well. So the state of the loop was like OCR system didn't work really well on the real scenarios because of the syntax. It was like synthetically generated images, and most of the data sets were trained on syntax. So they really hadn't seen real world scenarios a lot. So another problem in this whole loop of DocVQA and text caps was that the OCR extraction was done in an isolation from the application itself. So there was no feedback loop to the OCR system to improve based on like the errors that can happen for DocVQA and text caps. So the OCR extraction was like targeted as like a black box that you use it to extract out OCR and just pass it to DocVQA and text caps. So even if there was low performance on downstream OCR application, there was a disjoint that nobody cared like what happened on actual OCR application. So there was also not any real world large scale OCR data set available to make any progress on this side. So this led us to create text OCR, which was like collecting the OCR or like text tokens on complete text VQA dataset, which is 28K images. So because we knew that the text VQA and text caps images were very highly dense images in respect to the words, we collected very exhaustively like the word annotations on these. So we ended up with like 1 million word annotations, and each image has like 32 words. And this is like at the moment when we released the paper, this was last year. This was the largest same text data set on like the real images. So it has like 5x density compared to any existing data sets. So, why does it help? So the first question is like actually doing text recognition experiments. Like, so we saw that like on state-of-the-art models, like if you directly train on text OCR, it actually improves performance on text recognition across the board on all data sets. Like if you see row 2, we have actually improved performance on almost all data sets. And then if you use text OCR as extra data set while training your text recognition system, it actually also leads to improvement, which shows like text OCR like as a data set itself like is very useful in like when you're doing text recognition. So on the other hand, like end-to-end recognition experiments, we again saw that training on text OCR improves performance across the board compared to not training on it, or like training on Coco text, which was at the time like the real, the biggest syntax data set, including so this, if you add it with the synthetic data sets such as syntax, and if you add it and train it with it, you see much higher performance. So this was like actually quite high compared to the current state-of-the-art model for like end-to-end recognition as well. So this actually leads us to believe that like in some sense, like if we have these better trained models on GT OCRs, that could actually close the gap with text VQA and text caps. So this led us to like actually create a new model, which was like end-to-end text VQA model. Now like the OCR model was included inside the loop rather than keeping it separately as a black box. And we named it pixel MFOC because we were starting from pixels in this one. So this allowed us to like change a lot of inherent designs that were like coming through some prior assumptions that were not actually true. So we were able to test all these assumptions that we were making from start itself when we were treating OCR as a black box. So we ended up using better hidden states from OCR model, which again allowed us to achieve SOTA at that point of the time on text VQA. And it also allows us to training downstream aware OCR models, which are not treated as black box. So if there is some issue like in the word that is predicted by the text recognition model, the end-to-end recognition model, then you can basically fix it based on the feedback that you get from text VQA model. So you will know that your word prediction was wrong if you directly predicted it from OCR. And like text VQA says that this was the incorrect answer. So that gives you some like feedback loop here. Also, like it allows you to end-to-end fine-tune OCR model fixing mistakes relevant to a task, which is the thing I was just saying. So in practice, we realized that end-to-end fine-tuning is like very slow. So we actually froze the model for this particular aspect, but we have seen improvements if you fine-tune end-to-end the model. So, but in practice, it's very slow because the current models for like end-to-end recognition in general are very slow. So on text VQA specifically, like the left table shows how the baselines, the heuristics baselines that were introduced in the original text VQA paper improved by using GT OCRs. So the OCR upper bound is the row 2 is specifically what you need to look at. Like it jumped like to 67% from 45%. Like OCR upper bound basically means like if you only predict from OCRs, how well you can do on text VQA. So given GT OCRs, like the text OCR annotations, you can do 67% just by if you can properly predict from them. Everything else like increased a lot compared to it. So when you add like text OCR into the picture, the performance for M4C jumps from 40 to 48%. So this tells you that OCR was one of the problems that might have been fixed with text OCR, but there are still some reasoning gaps that are left in the whole picture. Like if it was really good, then it could have actually achieved 67% just by seeing text OCR, but there is still reasoning gaps that are there in the picture. So to wrap up, I will like to go through the challenges again. So to like basically tell the viewers about the listeners to the how exactly they can target this problem in future and what are the things that they need to focus on if they want to work on this particular domain of the problems. So in the open-ended vocabularies case, the current solution is still copy module in some sense to like copy the OCR text directly into it. So I don't think most of the models as of now fix any errors with the OCR text. So some sort of like added distance techniques can be applied here. So the multi-word prediction still relies on generators like the LM style generators to generate word question, like the multiple words answers as well as the captioning things. For text detection and interactions, we have text OCR now. So that's like the source of truth for like text VQA, but the question is whether it's like more generally applicable to real world scenarios beyond text VQA. So that's the question that's still not answered. For the text VQA ecosystem, yeah, you have GT OCS, but do you still want to consider whether this is actually applicable to more scenarios beyond this? So as an application, like at least for the blind sighted users, this is very important that it actually is applicable to the real world scenarios. For reasoning, we are still relying on model capabilities such as transformers and something else. And for world knowledge, we are specifically relying on priors that come with BERT or like any sort of pre-training that we are doing. And for coherent captioning, we are focusing on LM pre-training and like any sort of better laws that we can add here. So I don't think this talk is complete by mentioning the related work in the ecosystem, which has actually pushed this field much forward. So this includes like work such as STVQA, OCR VQA, and DocVQA, including from the organizers of these workshops. So there's been a lot of data sets that have come out since we released text VQA and syntax VQA in the start. So we actually use for everything that we have done here, we use our multimodal framework, which is like the center of framework, central multimodal framework inside Facebook, even used on internal tasks. So this is available at mmf.sh. And yeah, thank you for listening for this talk. You can explore text VQA, TextCast, and text OCR at textvqa.org and the MMF framework at Facebook research/MMF. And I would be happy to take any questions now.
Thank you very much.
Thank you for hosting me.
Yes. Is there any question from the audience? Oh, yes. Maybe you can see the chat. What is the sort of pre-training versus explicit knowledge for bringing the world knowledge?
Yes, so for explicit knowledge, I think this is a great question. And I think I really can't comment on it, but I can say what my personal thoughts are on it. I think the explicit knowledge has been tested well inside OKVQ and all of those and different data sets which specifically focus on adding explicit knowledge to the model. But as we move inside like larger and larger pre-training regime where like we have models which are pre-trained on like billions of image text pairs, like the recently released models from Google's, I don't think like we probably might not need explicit knowledge in like adding explicit knowledge in the future, because given this huge corpora, we will probably be learning all this from the biases that comes with pre-training itself. But yeah, explicit knowledge in itself, like adding it to the model is like a novel field, and it's not yet very well explored on how exactly you can add explicit knowledge to these models. So one idea around that is to have like some sort of like a copy module vocabulary or something like that for the external concept. I think that the follow-up is like for unseen concepts. Yeah, that's a tricky part. I think there is like a data set specifically focused on like unseen and novel concepts that's called NoCaps. And in that data set, Google has shown that doing like large scale pre-training in their recent paper that's called SimVLM, Doing really large scale pre-training also helps improve performance a lot on novel concepts captioning. So I think the point still stands, like if you have really large pre-training set plan, then you can probably generalize to unseen concepts as well.
Great answer. Any other question? Especially from the on-site people?
No. Yes. Okay. You can just speak louder. Okay. So thanks for your presentation. So I get two questions. My first question is: did you test so your model on test document, not on image natural cell?
You mean the pixel M4C?
Yes, you test your model on test.
No, not as of now. We haven't tested on DocVQA because we are specifically focused on the real images. Not like the doc images are real images, but like in sense of like Coco style images. So we haven't tested on them.
Okay. So my second question is, did you take care about tokens alignment or not?
Can you explain on what exactly you mean by that?
In your image, so you have so you detect a list of tokens like Volvo. And so do you take care of position of these boxes?
Yes.
Okay.
Yeah, so we feed positional coordinates as one of the inputs to the transformer model. So the positional embedding is updated based on that, and we make sure, like even in the copy module, that the orientation or like the ordering of the modules are same. Otherwise, the model will be randomly predicting through the OCR token. So that's one of the prerequisites that were actually added in the LoRa model, the original model as well.
Okay, thank you.
So any other question? No question from the on-site?
No.
Okay, so if so, I have actually many questions, but one main question is well, if you have now you almost have the perfect text VQA. So if we can use this, I think we can discriminate the relevant text and irrelevant text to the scene context. Sometimes some text in the scene is not so important for the scene understanding, and sometimes very important for the scene understanding. For example, the poster on the wall has gives no big information to understand the scene, but sometimes it's very crucial for the understand the scene text. So can you extend or utilize your ideas to understand the relationship between or importance of the scene text for the scene?
Yeah, so I think that's a very good question. Like, I think this is basically like introducing some sort of bias inside your model to figure out which OCR text might be like important. And actually seeing like this two heuristics in the row 5 and row 5, like the OCR biggest is like usually the answer like 1 out of 5 times, right? So this does say like the biggest OCR token would be mostly the answer if you like try to predict it without thinking about anything else. So we haven't like specifically tried introducing such biases, but I do know of like the some relevant work. If you like check out DocVQA citation that try to does it and actually performs really well on some specific categories of these tasks. So I think, yeah, there are some sort of like, of course, biases in these OCR models, but we specifically haven't like added any sort of biases to like focus on some sort of text. But I do think like when you add position coordinates for these OCR tokens, right? Like the model in itself, like the transform model based on the attention itself is able to figure out most of the time, like which would be the most important or like the biggest token in general for the input that is coming into the transformer. So like these biases probably might be getting introducing inherently that we haven't like specifically analyzed upon.
Yeah, thank you for your answer. Okay. Any other questions from?
Aman, this is Manish. So I wanted to ask, like, you said there is a feedback mechanism to correct the OCR. So do you start with the ground truth OCR annotations or you start with nothing and it starts predicting the OCR?
So there were like two ways we tried to do it. One was like start from the scratch and try to like do a joint training with end-to-end recognition loss. So that didn't seem to work a lot. So we actually tried to do fine-tune it using like text VQA accuracy directly, like first pre-training on GT OCRs and then fine-tuning it directly on the text VQA data sets. So yeah.
So if you started with the ground truth, could you see that the recognitions or detections were improving specifically for this task?
Not specifically. So we actually went back and actually saw whether like OCR accuracy was improving or not, but that was not the case. It was actually decreasing. So that led us to believe that maybe like text VQA in itself can improve its own accuracy based on that, but for general scenarios, that OCR performance was decreasing. So that's something that we haven't actually explored much upon, but that was a general observation, like adding text VQA loss and like fine tuning end to end would probably lead to decrease in OCR accuracy overall, because now it's more specific to text VQA rather than OCR data set itself.
Okay, thank you. Yeah.
And thank you very much. It seems time's come. Okay, let's close this session. Thank you.
Thank you.
Maybe next.
Is there?
Yes, hello, I'm here.
Hi. Okay, so maybe we can test the slides first. You can share this one. Yes, I can see it. Yes. All right. So hello, everyone. I am a session chair for this session. My name is Anand Misra. I'm a faculty member at Indian Institute of Technology, Jodhpur. It is my great pleasure to introduce Dr. Rizwan Lu, who is a principal scientist at Microsoft Azure AI, where she worked in invoice understanding, OCR, core engine, and video understanding in recent years. Her recent work on text VQA and text caption won the first prize of text caption challenge of visual question answering workshop at CVPR 2021. Prior to joining Microsoft, she was an associate professor in the Department of Computer Science at Texas. Her major publications appear in leading publications venues in multimedia and computer vision research. She was first place winner in many challenging retrieval competitions in Infographics for many years. She received 2015 Texas Presidential Distinction Award and 2014 College Achievement Award. She also received the Best Paper Award from ICME 2013 and ICMS 2012. She has obtained many competitive external grants from NSF, US Army, US Department of Defense, and Texas Department of Transportation. So she will be talking about her recent work on text-aware pre-training. Over to you, Zion, yeah, the stage is yours.
Okay, thank you so much for your nice introduction. Okay, good afternoon, everyone. I'm DC, and I'm from the Microsoft Cognitive Service. So today I'm very happy to be here to present one of our recent work on text VQA and text captioning. Thanks so much for Emerpret. So he already mentioned our work in his wonderful talk. So today I'm going to give you a more detailed introduction about our work, TAP, called Text-Aware Pre-Training for Text VQA and Text Captioning. So in this project, our major goal is to build an intelligent vision language model that can jointly understand vision, language, and syntax. So we focus on two major syntax-related vision language tasks, which are text VQA and text captioning. So Emerpret already introduced them a little bit in his talk. So for text VQA, the input to the system is an image and a related question, and the expected output is an answer in the natural language format. So you can see that is a little bit different from the document VQA. Is in text VQA, most of the images are natural image. They're not image about the document. And for example, in this case, given this image and the question, what number is on the bike on the right? So the expected answer is the number is 317. So the system needs to localize and understand the syntax 317 and use it as a final generated answer. And for the text captioning, the input is still the image, and the expected output is the natural language sentences describing the image, which is most likely relevant to the syntax that appeared in the image. So for example, given this image, text captioning may generate a sentence like a group of motorcyclists with number 317, 44, 30, 338, 598 racing outdoor. So from this example, we can see that both text VQA and text captioning require the model to read and understand vision, language, and the syntax appeared in the image. So jointly understanding vision, language, and syntax has many interesting applications. For example, such a system could help people who are blind to understand the surrounding and get useful information from the syntax. For example, to help them read the time from a certain screen. And also such a system could also be used to understand the document with image. For example, the system could automatically generate a description for the poster image. And the system also can help intelligent agent or robot to perform more complicated tasks. For example, a home robot may use the system to read and understand what's actually printed on the product, can help bring some specific kind of yogurt from the fridge by figuring out which one is a non-fat yogurt that we're interested in. So let us start from text VQA problem. I summarized all the previous major methods into the following common pipeline. So the input to the text VQA is an image and a related question in the text format. So since text VQA requires understanding 3 modalities, so all the previous work first adopt the single modality encoders to convert raw visual and text input into corresponding region and word representations. So to be specific, on the visual side, there exists a separate OCR detector and object detector that converts the input image into multiple detected OCR and object regions. To encode the OCR region, both the visual feature of the OCR region and the detected text are combined as the final representation for a certain OCR region. For the object, the visual feature of the detected object region will be encoded, and a language encoder is used to convert the input question into multiple word embeddings. So the output of the single modality encoders are the encoded region features for objects, OCR region, and the word embedding. And once we got the feature of each modality, joint modeling networks are designed to fuse these features together. It is expected that the output of fused feature can be directly used to predict the final answer. And this is done by including several extra layers of the output header decoding modules, which converts the fused feature into the final answer prediction. And once we got the final answer prediction, answer supervision is computed with the ground truth annotated answer and exam back prompt to update the entire framework. So we found the major challenging of text VQA is that it needs to jointly understand the information on 3 modalities: vision, language, and OCR syntax. So it's very difficult to align the description in different modalities that actually refer to the same or very closely related entity. So for example, still this example, the number on the bike on the right, the system needs to infer that the word number actually has a very close relationship with the detected OCR region that actually contains numbers. And we found many errors made by previous methods are related to the alignment failures. So they fail to align what information are usually related to each other. So for example, in this case, the state-of-the-art methods usually generate the answer 30, which is actually the OCR region appeared in the bike in the middle instead of the right one. So we think this kind of failure is related to how previous methods are trained. All previous methods are trained with the final answer supervision alone, so which enforce the generated answer to be exactly the same as the ground truth human annotated answer. However, this answer supervision do not explicitly enforce the required cross-modality alignment, which is very important for text VQA. So the key is how to train the model to generate the better fused features that contains better cross-multimodality alignment. So let us take a closer look of this example. What kind of a cross-modality alignment we need to learn to answer the question, what's the number on the bike on the right? So the first we need, there need to be some alignment between, words and certain vision regions, either the word number with the OCR region, such like 30 or 317, or the alignment between the word and the certain visual object regions, such as the bike. And sometimes the system also need to do some more fine-grained alignment, like the bike on the right refers to some specific bike that we are interested in. And we summarize this alignment as visual text alignment. Other than the visual text alignment, it is also important to align OCR region and object region. For example, in this case, it's very important to understand the OCR region 317 falls on the bike that we are interested in. So we call this as OCR object region alignment. So the failure of building any of this alignment might lead to the final incorrect answer. So our goal actually is to introduce some actual intermediate objectives directly on the output feature generated by the joint modeling part, and trying to generate better fused feature to well align visual text alignment and OCR object region alignment through pre-training. So for this purpose, we propose text-aware pre-training TAP for aligned representation learning. So in the pre-training stage, we design various syntax-aware pre-training tasks to help joint representation learning between text word, visual object, and syntax. In the fine-tuning stage, we initialize the model with the pre-trained weights and train the model with the question answering or captioning loss. So in this study, we focus on how to make the pre-training effective for syntax vision language tasks, which we refer as a text-aware pre-training. So we build our framework upon M4C, which is a transformer-based architecture that consists of 3 previous mentioned modules. So single modality understanding, joint modeling, and the output head. The input to the system is an embedded question text token, the encoded OCR regions, and encoded object region detected in the image. So correspondingly, we design multiple pre-training tasks in order to align, text word to vision image shown in the blue arrow, and to align the object region and the syntax region as shown in the orange color. So to align text word and the vision region, an intuitive starting point is to borrow the pre-training tasks from natural language processing and vision language pre-training. So namely as the master language modeling and the image text matching. So however, we find directly adopting these 2 tasks show no improvement on text VQA. So we find that the major reason is the question contains very limited syntax related tokens. So the model tends to overlook the syntax word and regions during the pre-training, and thus shows very limited improvement. So to address this issue, we propose to include, the text syntax and object words as the additional text input. And we also update the mask generation and the sequence polluting methods accordingly. So for mask language modeling on the extended text, we randomly mask each text token with a probability of 15%. So the masked words are replaced with a special mask token 80% of the time, a random word 10%, and it remains unchanged 10%. So the mask language modeling task takes the fused feature at the masked position as the input and aims to recover the masked word. For image text matching, input text is polluted 50% of the time by replacing text subsequence with a randomly selected one from another image. And the image text matching task takes the sequence feature as the input and aims to predict if the sequence has been polluted or not. Other than vision text alignment, text VQA and captioning also pose challenges on understanding the spatial relationship between vision regions. For example, understanding, the company name course-like has some spatial relationship within, the object screen. So to encourage model learn such spatial relationships, we propose a new pre-training task named as relative position prediction. So the input to the pre-training task is a randomly sampled vision object feature and the syntax feature. The objective is to predict the relative spatial position between the two sampled regions. So we start with a very simple relationship of whether, the syntax region is on the object, and thus model the relative position prediction as a binary classification problem. And we then extend the task to a 12 plus relative position prediction problem with the class on, cover, overlap, 8-way relative orientation, and unrelated. So we conducted our experiments on several text VQA and text captioning benchmark data set and used their standard evaluation metrics. So for the text VQA, the original data set contains about 22K training images. And the syntax VQA is another data set for text VQA and has about 18K training images. And text captioning is a text captioning benchmark data set, which augments the image in text VQA with 5 OCR captions per image. So here we show some comparison experiment results between text-aware pre-training and non-text-aware pre-training only. So other settings are the exact same. So the experimental results show that by just ending text-aware pre-training, the performance of the model already significantly improves on both text VQA and text captioning tasks on all of 3 benchmark data sets. And another advantage of pre-training is that no answer annotation is required during the pre-training stage. So to unleash the power of our text-aware pre-training, we generate a large-scale syntax-related image caption dataset from the conceptual captioning dataset, CC. So we end up with the CC OCR dataset that contains more than 1 million images with syntax. So specifically, we discard CC image with no detected syntax or with watermarks only. We then use the selected images for pre-training. So the upper figure shows the number of syntax word detected in original CC images, and the bottom images are examples of the discarded and selected images from CC. So with pre-training on this large CC OCR dataset, our method outperforms the state-of-the-art by a large margin. So the red bar is our baseline method that shares the same network architecture. The blue bar shows the performance of previous state-of-the-art, and the yellow bar shows the performance of our approach. So this figure shows some representative failure cases of a non-text-aware pre-training baseline that can be corrected by text-aware pre-training. So in figure A, the model answers who must survive by the syntax, the Yam must survive in the image. So text-aware pre-training shows a good performance on challenging questions that require understanding over text regions. And text-aware pre-training also performs better on questions that need aligned syntax region and object regions. For example, in figure B, the model grounds, the object region, the jacket on the man pointing, and generate the correct answer, Raymond, with the syntax, the Raymond football leagues on the man's jacket. And figure C shows an example that text-aware pre-training correctly understand the relative spatial relationship in question. What's the company name on the left to the cross logo? And furthermore, text-aware pre-training helps the model read a large piece of text. For example, in figure D, the model correctly answers the question of who edited the book by finding the editor's name, full name in the syntax. And this figure shows some examples of multiple questions on the same image. For example, in the E, what number is on the bike on the right and what number is on the middle bike? And the E, G, and H shows, what's the advertisement in the right whiteboard and what's the number of 1,000 homes. So this example shows that the model selects the correct syntax region as the answer based on the input questions. And also this table shows the co-references scores with and without text-aware pre-training. So these numbers represent the attention score between two semantically corresponding tokens averaged across all such token pairs in TextVQA. So higher co-references scores imply a better aligned representation. So in the first two row shows that text-aware pre-training improves the syntax language co-reference scores by about 7 times. And the bottom 2 rows show that text-aware pre-training increases the syntax visual conferences scores by 2 times. So this increases validate that text-aware pre-training successfully learns the latent alignment and thus improves joint representation learning. And furthermore, this figure visualizes the attention score between a text word and all visual regions. So quantitatively, we observe a higher attention score with text-aware pre-training showed in the bottom row compared with a non-text-aware pre-training baseline. So for example, in figure A, text-aware pre-training grounds the text word must and survive to the corresponding syntax region with much higher attention score. And we also attended the text captioning challenging in 2021. So far, our approach is still ranked as the #1 in the competition. And our result actually is much better than other submission result. And in this competition, we also made a couple of modifications over text-aware pre-training to improve its performance. So for example, we used some stronger visual feature from the WinVL, and we also boost the OCR detection result by using 2 OCR detector, Rosetta and Microsoft OCR. And we also enlarged the transformer layers from 12 layers to 24 layers. So now the performance on the text captioning in the testing data set, we can reach 109.69. So in conclusion, we propose text-aware pre-training for TextVQA and text captioning. So the model significantly improves the performance of syntax vision language tasks by generating a better joint representation between text word, visual object, and the syntax. So this work has been published on CVPR 2021, and we have released our code and a data set here. So for more information, please come and chat with us. Okay, thank you so much for your attendance, and I'm happy to take any question.
Thank you, Joan. So we have some time for questions from on-site and as well as you can type here.
Okay. Sure.
So You talked about, so maybe I may ask one question. So you talked about explainability or like attention. Can you explain that a bit more?
Oh, so your question is regarding to our experiments on the extended text?
No, on getting attention. You have some slide, I think. Attention over text. How do you get that?
Oh, how to get the attention, right? Here. You're talking about the attention score we get about the text word and the syntax region, right?
Right.
Okay, yeah. So so basically, yeah, we can from like, you know, it's kind of so for each prediction, actually, you can get a kind of, you know, attention score, right, from the transformer. So we try to do some attention score analysis between a different, for example, between the syntax region, between the object region, and also between the word. So here we just show some experiments where they try to show some attention score between, you know, the word from the question and also with the syntax region. So we detected by the OCR. So in this example, for example, in the A, who must survive. So the baseline, we can see that is attention score between this word must and survive with the corresponding like OCR syntax region here actually is pretty low, but after to do the text-aware pre-training, we can see that is because the model through the pre-training task, the model is kind of like forced. Actually, yeah, the pre-training task forces the model to correspond, you know, the word and also the syntax region more closely. So we can see the attention score between them has been increased a lot. And also here in this example, so what's the company name to the left of the Cougars logo? So we can see that is here is the word Cougars, and here is also the syntax region detected by the OCR. So without the text-aware pre-training, we can see the attention score between these two parts. Between the word cougars and its corresponding syntax region is lower, but after the text-aware pre-training, the attention score has been largely improved. So by doing such analysis, we just try to validate or to show in visual that, you know, by doing the text-aware pre-training, the correspondence between, for example, there's word and the syntax region can be largely improved.
So Amanpreet has a question. Can you expand on OCR types in the second last slide?
Oh, here?
Yes, I think.
Okay. Yeah, actually. So first I want to say, as I think as the Amprit introduced that, we also find out, you know, for the text VQA and text captioning. So the OCR result actually is very, very important. So if we can get a better OCR result, then the performance is going to be improved as well. So for the OCR detection in our CVPR 2021, we used the Microsoft OCR. So the OCR detector built in our team. So the result actually is pretty good, but we still see there's some failure cases which couldn't detected by the Microsoft OCR. So in this challenging, we used a true OCR detector. So the Rosetta is from the Facebook, and we combine both OCR actually together. So you can imagine as if both OCR detector to recognize that region, then we have a high confidence that, you know, that is a good one. But for some OCR region may be missed by Microsoft OCR, but captured by the Rosetta, or some OCR region may not be captured by Rosetta, but captured by the Microsoft OCR. So we can capture both. So in this challenging, we use both OCR detector, try to improve the OCR detection. So from the result, we can see that is on the validation set. By using the stronger OCR detector, the performance also can be improved as well.
Yeah, so my question was about the OCR type that's in the row 4.
Oh, row 1, right?
Yeah, like in the
OCR
table,
type.
it's row 4. Yeah.
Yeah. It is a little bit complicated question because we find out, sometimes, for example, if we encode the syntax answer word, for example, we detect some syntax in the image, and if we encode the syntax answer word as a fixed vocabulary, actually the performance will be affected. So in this challenging is we didn't encode the syntax detected in the question as the fixed one. So we didn't do that, but after some experiments, we find out is okay, the performance actually improved without it. Yes.
Okay, thank you.
Thank you.
With that, I think we are end of time. Thank you, Iswan, for your nice talk. Thank you very much.
Thank you for your attendance. Yeah, so if you have any detailed question, you can refer to our paper at CVPR, and also our code and data is here. And you're welcome to email me if you have any other question. Thank you so much.
Okay, we have a 2 minutes break to set up the panel.
I have a couple of minutes to set up, and we'll continue with the panel. Right.